All right, we need to talk about the mean and standard deviation, or variance, which is the standard deviation squared of a random variable. So if you look at this, this is a made-up lottery ticket. So you can either win $0 or $500, okay? And the probability of winning 500 is 1 in 1,000, and probability of losing and getting nothing is 999 out of 1,000. So if I bought 1,000 tickets, I would expect to win one time. I average, that one win gets me $500 per 1,000 tickets. And so the average money that I make per ticket is 50 cents per ticket. That's a long run probability, okay? Because I'm not going to win on the first ticket at 50 cents. I'm not going to win on any of the tickets 50 cents, but in the long run, my average would be 50 cents per ticket, okay? And so you can think about this, like if I were selling these tickets, I would want to sell them for at least 50 cents, or I'm losing money as a lottery. If I sell them for $1, I'm making $500 every 1,000 tickets, which is pretty sweet. All right, I'm making 50 cents a ticket. So anyhow, this is the idea that we're getting into, is the mean, and then we can also talk about the variance, right? So most of the time you're actually making 0 cents per ticket. Sometimes you're making $500 per ticket, okay? So there's a lot of variability around this 50 cents. It's not really 50 cents, but there's some variability around it. How do we measure that, okay? This is clearly not a normal distribution because it's a huge stack at 0 and a tiny stack at 500, okay? But there's still a standard deviation and a variance that we can measure. So when we look at that, the mean of a discrete random variable, basically what you do is you take these numbers, the value, and since this is a random variable, all of these are numbers. That's why it's important that we have random variables and not just any probability model where this is like heads, because heads doesn't have a value. It just either is or isn't, okay? So the value times the probability gets x1, p1. So you multiply this times this, and that goes there. And then you multiply these two, and then you add it. And then you multiply these two, and then you add it. And you keep going until you get to the very end. Multiply them and add it. And then you get the sum of all of the xi's, pi's. This is the mean of a random variable. It's also called the expected value. And back on the last slide, do I actually expect to make 50 cents per ticket on a single ticket? No. But it's in the long run, this is what I expect to make on average, okay? So it's a mean, a long run expected value. The variance is a little weird, a little bit different, okay? And a little bit messier, as you can imagine, okay? But what we're doing is we are taking the sum of every xi minus the mean. So this is like my deviation. And if we just added up all the deviations, we would get 0. So what do? We square them. Okay, so the deviation squared. That's not unusual. Take this value, x1, minus the mean. Take x2 minus the mean, and you square it. You square it, okay? All the way until you do x, the last one, minus the mean, and you square it, okay? Then we would normally add them up and divide by how many. But, like, let's say there were 100 of them. If this is a 30% chance, then we would have 30 out of 100. And this would be, if this was a 20% chance, it would be 20 out of 100. And if this was a 10% chance, it would be 10 out of 100. And you can see that they'd all have a common denominator of 100, just like these probabilities all have common decimal places, okay? And this is just counting. So it's weighing the ones that have higher probability 50 times and 30 times and 20 times, okay? Relative to one another. So these probabilities account for adding up and dividing by how many, okay? We add up and you multiply by the probabilities of each of their squared deviations, okay? And that's your variance, which is why you don't see this divided by n minus 1, because multiplying by a decimal is just like division, okay? So you add up all the deviations squared times their individual probabilities. So order of operations, subtract, square, multiply. Subtract, square, multiply, subtract, square, multiply everywhere, and then you do all your addition. Last, this sum comes last, and take a square root, and you have your standard deviation. So, for example, okay, so Linda's been selling cars, and in her first 50 days, she sold 0 cars on 30% of days, and 1 car on 40% of days, and 2 cars on 20% of days, and 3 cars on 10% of those days. Okay, and so this is her probability model that she's sold. What is her average number of cars per day, the expected value? So I would multiply these and I get 0. So I'm just going to multiply the products and write it right below. Here I get 0.4, 0.4, 0.3. I add them up and we get 1.2. That is the mu of X, capital X. That's the number of cars per day. All right. Standard deviation is going to be a little bit messier because I need to take 0 minus 1.2 squared times 0.3 plus 1 minus 1.2 squared times 0.4 plus 2 minus 1.2 squared times 0.2 plus 3 minus 1.2 squared times 0.1. Okay, and it's kind of a mess. So I just took a picture. All right, so notice the 0 times the 0.3. These are the 4 numbers that I calculated to get my mu, which I added wrong. 1.1, Mr. Crayons. Thanks for catching my mistake. Photograph. All right. And so we take the deviation squared times the probability. 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 And then we add them all up. And this is the sum of all of them. And we get 0.89. And if I wanted the standard deviation of the model, it would just be whatever the square root of 0.890 is. Okay. So that's a mess. All right. It's messy formulas where you're adding up lots of things, and it's really like for these discrete cases and stuff like that. All right. We'll talk more about that in a minute. But what I want to discuss, or in the future videos, and you'll try it on homework and we'll do it in class, but I want to also discuss the law of large numbers. We've talked about this before, that these rules only apply for the average of many, 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 many trials. It tends toward the true mean in the long run. That's the big idea of it. And I talk about how there's a dwindling influence. The more trials you do, the less it's able to fluctuate your overall average. And the reason why it works is because the next n trials tend to be relatively close to the mean. So here, let's do a couple more dice. All right, so if I roll 4 dice, then the average of the roll should come out to 14, okay? And if I just roll, let's just roll 10 times to start, okay? You'll see that my rolls are kind of all over the place. Sometimes they're below 14, sometimes they're right at 14, sometimes they're above 14. So the yellow dots that I can get rid of are the roll totals, okay? But notice there's a lot of fluctuation early, but that starts to go away, especially as I roll more and more, okay? And it starts to level off. This one didn't even have a lot of initial fluctuation, but as you zoom out and you see how flat this is, look how steep those adjustments look. Okay, so if I do this now 100 times, you'll see lots of rolls, and it just really just tends to flatten out. Ooh, it's actually going away a little, but hey, guess what? The next 50 rolls are going to be close. Oh, look at that. It got right back on that line, and you do it. It might go away a little bit, but in the long run, where's it going to end up? Very, very close to the true mean. Oh, wow, that must have been a streak. Ready? Here, if I show the roll totals, see how this got dragged up right there? What do you think we're going to see when I show the roll totals? A bunch of rolls right in this area that are all up above. See that? And down below, there's not much down here because there was just a sequence randomly, right? Streaks happen when you're randomly rolling where there were lots of numbers above and not that many below. Okay. And then down here, see how it's sloping down because you're seeing a bunch below, but there's only like 1 or 2 up above here. Okay. And so there's this relatively symmetric picture of the distributions. Okay, you're most likely to get things closest to 14, tend to get some unusual rolls a little further away, but it all comes out to that average right there. All right, so good luck and farewell.